Welcome to the lecture series. In this lecture series, we are going to discuss about the Nyquist plot and the Nyquist stability criterion. Nyquist plot is nothing but a graphical method used in a control system to analyze the stability of a closed loop system by providing the frequency response of its open loop transfer function. It shows the real and imaginary concepts of g of j omega and h of j omega on a complex plane as a frequency varies and stability is determined by counting how many times a plot encircles the circle. Now, in this lecture, we are going to discuss about how we visualize the Nyquist plot, how we analyze the stability margins, and how we apply this stability criterion. So, before getting into the Nyquist plot application, we will discuss the basic parameters, how it is represented and how the behavior is analyzed and how the insights of this Nyquist plot applies for the applications. So first one is parametric representation, and Nyquist plot is a parametric plot where the real part of an open loop transfer function is plotted against its imaginary part. And here we have the complex plane also. The plot is drawn on the complex plane with the x-axis representing the real part and y-axis representing the imaginary part of the frequency response. And coming to the open loop behavior, it shows how the open loop transfer function behaves with the real part marked across the imaginary part. And next one is frequency response. Here the frequency response omega is an implicit variable sweeping from minus infinity to plus infinity, which allows for more complete representation of the system behavior. And coming to the simultaneous insights, it reveals both the gain and the phase information, and it is crucial for the stability analysis. And visualizing the Nyquist plot, here you can see we have an plot against the body system. Here we have the lower frequency, typically real and positive, starting the curve. We have the higher frequency. Here the gain diminishes towards the zero, causing the curve to approach the origin. The plot encodes the system dynamics and offers critical behavior stability insights. So here we have an RC circuit, and here it is the both Bode plot and the Nyquist plot is marked against for this sample circuit. And here we have the key characteristics also to apply this Nyquist stability criterion. So before getting into that, we have to know what is the stability problem. So in the closed loop stability, the directly ties to the poles of the characteristics equation. And second one is right half plane poles. So here the poles are located in the right half of the plane, indicating the instability, leading to exponentially growing the outputs. And next one is complexity of the pole calculations. And now we're getting into the steps to apply this criterion. First step, we have to identify the open loop poles, determining the poles in the right hand side, and draw the Nyquist plot while considering the L of j omega over the Nyquist contour. Now counter the encirclements, count the clockwise encirclements starting from -1 plus j 0. Calculate the closed loop poles, that is it is indicated by j is equal to n plus p, where j is the zeros and p is the poles, and n stands for Nyquist stability constant. And next one is access the stability. If z is 0, system is said to be stable. So these are the practical steps which apply for analyzation and for the stability criterion. And next, with the examples, we can analyze the stable system of the Nyquist plot and unstable system. In the stable system, the system here the no open loop poles in the right hand side. So first problem is solved here, and the plot makes no encirclement. So second problem is also sorted out here. Therefore, the closed loop system has no unstable plots and it is stable. The system mechanism does not destabilize the system. It maintains the stability. Well, coming to the unstable system, here you can see there is no open poles in the right hand side. The plot makes one clockwise encirclement. So first problem is solved, but second condition, we have one clockwise encirclement, and here it's said to be has one unstable pole, and thus it leads to an unstable system. So here you can see we have bounded input signal and the system response like bounded and bounded output. If the system is unstable, we have bounded input and we have the unbounded output. So these are the few terms you have to get clarify. So here you can see for the stable and unstable system, we have the ball in the stable condition where it is finally comes to a stable for the period of time. For the unstable, it goes for the infinity. We cannot say whether whenever the system is said to be steady state condition. So here also we can gain for the gain margin and phase margin. So as previously discussed in Bode plot, here the gain margin can be increased before the Nyquist plot encircles, and in phase margin it indicates the additional phase lag that can be tolerated at the phase gain crossover frequency. And for the last time for understanding the system stability, we have to go for the mathematical modeling, and also we have to get for the unity feedback system analysis. Thank you.